Today we're going to be talking about equipotential lines. First, I want to start by breaking the word up into two parts. First, we have this part equi, which I like to think of as meaning equal. Then you can look at the second part, potential. Oops. Now we're going to just keep that as the word potential. But it's important to note, what kind of potential are we talking about? In this case, we're talking about electric potential, which is also equal to voltage. So now that we've broken apart the word equipotential, it's easier to remember that when we're talking about equipotential lines, we are actually talking about how we can visually represent the voltage and how it stays the same around a charged particle. We're going to draw these field lines. There's one. There's two. Alright, so we have our positive charge, and now we have our field lines that go out of the middle. We note that it's a positive charge, so the electric field lines are going away from the charge. Now to draw the equipotential lines, we're simply going to draw a circle around this positive charge with an even radius. So those circles, the blue lines, are what actually are the equipotential lines. So they represent how the voltage stays the same. We want to look at next at an equation here. And it's that V equals KQ all over R. The V represents voltage, K is a constant, Q is the charge of the particle, and R is the radius. Now we can see if we have a dot that we place anywhere along these lines. Let's say it's here. We can move this dot anywhere along this equipotential line, and the voltage will stay the same. That's because if we look at this equation, your K is a constant, so it will remain the same. Q is the charge of the particle, which also will remain the same. And the radius that goes from the particle to each of these black dots stays the same in this circle. So if all three of these elements are staying the same, the voltage is not going to change. So let's work through an example with this equation of V equals KQ all over R. K is a constant, like I just said, that's equal to 8.99 times 10 to the 12th. For this example, just to simplify it, let's say that the charge of the particle is equal to 1. And that the radius is equal to 0.005 meters. If we plug this into the equation and we're looking for the voltage, we're going to get 8.99 times 10 to the 12th, all times the charge of 1, divided by 0.005 meters. Now if you plug that into your calculator, you get that the voltage is equal to 1.798 times 10 to the 12th. So that's how you would use the equation of V equals KQ over R. Now, if we want to talk about the work, that also can be represented by these equipotential lines. The formula for work is that it's the change in the potential energy, which is also equal to the charge times the change in voltage. So if we come back up here to the circle, we learned as we go around the circle, as we look at each of these dots, that the voltage never changes. And so the change in voltage is going to be equal to 0. Now if we have this charge times 0, anything times 0 is equal to 0. So overall, the work of moving a dot, or finding the work around an equipotential line, is 0 because the voltage never changes. So now we're going to draw, or I'm going to show you one more picture. And this comes from our textbook. Get a little bit bigger. So I like this image because it shows that there's two particles that have opposite charges, but they're equal in magnitude. And that can be important. So given that the electric field lines are these ones that go out, they're the blue ones with the arrows that go from the positive, away from the positive charge and towards the negative charge. So the equipotential lines can be drawn simply by making them perpendicular to the electric field lines. On the other hand, if you're given the equipotential lines, as in this figure, the electric field lines can be drawn by making them perpendicular to the equipotentials. So if you're only given either one equipotential lines or electric field lines, then you can easily draw the other one just by making it perpendicular. So I'll just highlight that really quick here. So these lines right here coming out of your positive charge, those are your electric field lines. I'm not going to highlight all of them, I think you can see them. But these circles here going around the inside, these are your equipotential lines. Note how they are perpendicular to one another. And so that's an important principle to remember, that the electric field is always perpendicular to the equipotentials. There's one more term that I want to teach you, and that is the idea. So we've been talking about equipotential lines. When we're talking of equipotential lines, that is referring to two dimensions. So just like these images I've been showing you, how they're flat, we can draw the lines. If we're talking in a 3D sense, then it becomes an equipotential surface. Both are perpendicular to electric field lines. It's just if you're talking about 2 dimensions or 3 dimensions is whether you say equipotential lines or surface. So let's do a quick review. So we started with the word equipotential. We broke it apart into 2 roots, equi and potential. Equi is the same as equal, and the potential here is electric potential, which is also our voltage. We drew a figure by drawing a positively charged particle. We drew the electric field lines, which are represented in purple, which go away from the positive charge. We then could draw in the equipotential lines, which are blue, as they are always perpendicular to these electric field lines represented in purple. We talked about how the voltage always remains the same anywhere along one of these equipotential lines. That's because of this formula, that voltage equals kq over r. K is a constant, so it will always remain the same. Q is the charge of this particle, which will always remain the same around this equipotential line, and the radius is also the same. Which radius we're talking about is from the charged particle out to the dot that you're drawing on your equipotential line. Hence, if that radius is always the same, your voltage will remain constant along an equipotential line. That's an important principle to remember when you're thinking about work, because work is equal to the change in potential energy, which is also equal to the charge times the change in voltage. Because the change in voltage is 0, that also means that your work is going to be equal to 0. This picture illustrates the importance of how you can draw your equipotential lines and electric field lines, as they are always perpendicular to one another. And remember, equipotential lines is when we're referring to things in the 2D or 2-dimensional. An equipotential line or an equipotential surface is when we're referring to things in 3 dimension.